I'm hoping this text size is good. Let me know. This actually could go up a little bit. Let me know if I need to increase the text size for you. I'll do, yeah, we'll do that. Just put a plus in the Slack thread if you want me to increase the text size, and I'll do that. All right. So first off, I want to start off with a little recap, just talk quickly about what we went over yesterday and get to where we left off. And we left off on how to program, I believe. So we talked a little bit about the language details. We talked about kind of the role of Python in data science, which is that Python is the most common language to see implemented in data science as a general purpose language, which that's another detail of Python, is that it's a general purpose programming language. Sorry about my typing. I'll get used to it. Yeah, so general purpose just means that it's Turing complete, meaning it can model a complete set of, let's say, a complete set of computational tasks. It can model what we would think of as computational algorithms fully, solve a wide variety of problems. Okay. It's also an interpreted. It's also an interpreted language. Interpreted languages are nice. They're simple. They have sort of a simplicity in terms of the way you can work with them. You know, your source document and your executable are the same document. So again, this is a Python file that I'm working on, a Python file that I'm working out of right now, and this is literally the document that I will execute when I run my code. So yeah, so that makes it, you know, kind of simple to work with. It's in interpreted languages can be used to script. You might have heard of scripting languages. So scripting is when you have another program that can be controlled via a script. So a lot of times interpreted languages are called scripting languages, and that's, the Venn diagram is close to a circle with that, but it's they're different terms for different reasons. That's kind of how I see it. But so there are various other programs that can be scripted, can be controlled with Python and things like that. And that idea is sort of you know, behind a lot of things that you'll interact with in your career as a programmer, right? You can think about, you know, building a building something in a Jupyter notebook as scripting the program Jupyter notebooks, for example. It's a little bit reductive, but yeah, that's an analogy. Okay. We also talked about comments. So again, everything you see here is in a comment. If I run this code, just literally nothing is going to happen. So I just ran my code and we didn't get any output. This is just, you know, letting me know that it's over and that it's going to watch for any changes. If I change something here, it's not going to happen. So that's because everything here is commented out, right? So comments are useful for taking notes in your code and documenting parts of what you're doing. They're also really useful for turning on and off parts of your code, right? So let's say you want to isolate some part of your code and you comment other things out and you just want to see how one little part of it works or something. So you can turn off other parts of your code by commenting those parts of your code out, and then sort of isolating different pieces that way. So you'll hear that a lot. Okay. We also went over this overview. So like the major topics, one way of breaking this up, and this is a little reductive, but this is one way of breaking up learning a language to the point of being proficient enough to be able to solve problems and kind of, it's a good basis from which to expand, right? So this does not cover every programming topic or every programming topic in Python, but it's the foundation that you'll use to expand into every topic that you're interested in. So this overview includes evaluation and execution, which are kind of, some notes on that would be, let's see, that Python is an interpreted language. Another example would be when Python executes a script, when it executes a Python executable document, just like you and I, it starts up at the top of the document and reads left to right, top to bottom. Well, I'd say just like you and I, presuming that, you read English in that manner, right? So that is also the way that Python parses and reads a document, right? So if I have code here on line 21, let's say I print hello, and then I print hello world, right? So the code above will be executed before the code below. So there's an order to the program. Starts at the top, goes down to the bottom. So if I run that, I see hello and then hello world, just like I asked it to do here. So yeah, let's say left to right, to right. We could also include inner to outer, and this is a concept we'll kind of come back to later, so don't worry if that seems out of the blue. It is out of the blue for now, but if I'm gonna try to be accurate about execution order, inner to outer, you think about PEMDAS if you're familiar with order of operations in math, something like that, and we'll cover, like I said, we'll cover that later. So inner to outer, left to right, top to bottom. So yeah, so these are questions of how is the document evaluated? How does it run? What are the details of how the language runs, right? We could get into other things like memory model and type system. And if you're familiar with those concepts, I would personally categorize those in this category. Types, we talked about this. We want to be able to deal with, for example, we want to be able to deal with text differently than we would deal with numbers. And we're about to dive more into those details soon. Abstraction is a way of capturing values, or capturing values or processes, something like that. Conditions allow us to write dynamic code, and iteration allows us to repeat processes. And we haven't gotten into any of these, but we will be getting into these shortly. And I'll sort of try to wrap up with today's lesson at the end and just quickly like kind of show which category I would put everything in. Okay, let's get into it. So last time we left off on how to program here. So how to program in one lesson. So think about the problem, define what it means for the problem, for the program to be working, define a success case, right? Create a series of formal steps that lead to repeatable operations. These, every time I read these, I think, wow, these sound so on the nose. Like, how am I going to justify to this class that I'm reading to that you should think about the problem like that? How am I going to justify me saying this, right? I don't think it's a problem that, you know, people like just, they're like, oh, I'm going to just, it's not working, you know. I don't think that's really what's happening. The second one, though, particularly, define what it means for the program to be working. It's easy to overlook. It's easy to overlook, like what it means to like have successfully solved the problem. So there's sort of a test-driven development way of thinking about problem solving that I'm going to tie back into with this concept a lot. I'll be touching on this concept a lot. And it's something that I notice from a couple years of working with students here at Galvanize, that this particular thing, for, I think it's safe to say for most people, needs some work, right? So one habit that I think is worth breaking in order to kind of get to this point is, what I will notice is that when people are learning to program, they'll want to do this thing. And I wanted to do this thing. And I've seen other people where you start at the top and you go, you know, to the bottom. And then once you've reached the bottom, you're finished. So this is a counterintuitive thing, but where I start is here. I start at the end. I start at whatever I'm doing, it better end up like this, right? The very first thing that I do when I'm solving a problem is, what does success look like? What does a working solution look like? And I'll take some notes. I might write some comments. Yeah, I'll just kind of draw up a little bit of a schematic of what I'm expecting this to look like. And it can feel really unnatural to start at the end and then move back up to the top and kind of work, you know, outside in and then inside out and then top to bottom. There's sort of a pattern there that takes some habituation to get used to. So that's that's a really typical thing, and I think it's sort of a weird when you're just starting, because, you know, when we're writing a document, often, you know, just writing in a word processor, writing on paper, you know, you're writing from top to bottom, and that pattern can be hard to kind of shake loose from. So I want to plant that seed early. You know, when you're programming, you tend to be working in the middle of the document somewhere. It might sound like obvious or something, but I think it's worth thinking about now so you can get used to it. Okay, cool. Create a series of formal steps that lead to a repeatable operation. This is just kind of the actual problem solving, kind of getting in there and doing the algorithm. Okay. So thinking about the problem, broadly define what you're trying to do. This ties back into what I was saying about where do we want to end up. Is there a specific outcome that you need to obtain? What does it mean for the program to be working? So prior to writing any code, understand what a solution or what a success in your program would look like. Is it supposed to print something? Are you creating a new variable? Are you changing an existing variable? Are you returning something from a function? We'll get into those things later. Creating a series of formal steps. So think about how to obtain a working solution in small, definable steps. This is a good point here. One thing that's easy to get tripped up on is, like once you think, oh, this is my goal, it's easy to accidentally skip steps. I think in the name of keeping things simple. But if you skip steps while you're coding, Python's just not going to be able to execute your code. So it's okay to take small steps. It's okay to write a line of code that does one little part of your program. It does one little part, gets you a little bit closer to a solution. Often that's just the most effective way to solve problems. Just one little thing, 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 and then you're done. So don't be afraid of taking small steps. If necessary, write pseudocode. So pseudocode is just basically, a description of the algorithm you're going to implement, just in comments. Write pseudocode that describes a general algorithm of what you're trying to accomplish. Write code, as in translate pseudocode to Python. Funny thing about this, there are formal pseudocoding standards. Every formal pseudocoding standard I've seen is more verbose and often less elegant than Python itself. So I've seen formal pseudocoding standards like implemented in for C, for example, and I'm like, I'll look at them and I'll think, why not just write this in Python? Just make the pseudocode Python. So the paradigm in Python is that Python is a self-documenting. The code is what we think of as self-documenting, quote unquote, which means that, the language is built to be readable and, that when you read it, it's intelligible as to what it does. Now, obviously, when you're learning, it's not yet intelligible. So, you can write pseudocode to kind of get you by. But I know some people are likely coming from backgrounds or, they're aware of other languages where pseudocoding is the norm. It's, where the culture in that language is that you should pseudocode everything. The culture in Python is that you should pseudocode nothing unless you have a really good reason to justify that. Learning is a perfectly fine reason to justify that. But in the end, ultimately, you're probably going to want to get away from pseudocode patterns. Okay. Cool. We got a little breakout here. So write an algorithm for boiling a box of spaghetti. Yeah. You didn't see the solution. I didn't. Okay, good. So I'm going to, let me see. Okay. That's in Slack there. I'm going to put 5 minutes on my phone timer. And go ahead and just like write a list of steps. It can be kind of a bullet pointed list, like, find spaghetti, Um, boil spaghetti, right? So one thing you might find here is that, your solutions, may be more or less detailed than other people's. And, this is just a basic kind of algorithmic exercise. So there's no right or correct way to do this, but, you could even think about it. You could think about it in a generic sense, like how would somebody in any kitchen boil a box of spaghetti, or how would you in your kitchen boil a box of spaghetti? So there's a number of ways to take this, and that's all fine. I got 5 minutes on the clock, and just go ahead and write your list of steps. And once it's done to your satisfaction, go ahead and paste it in Slack. Also, this is a good time. If you have a question, feel free to just put it in Slack. You can at me and I'll see it. So if I say at, um, oops, that's not, that name looks like my name, but that's not my name. Okay. Oh my gosh. Let's see. Okay. So if you put an at in front of my name there, I'll be more likely to see it quicker. Okay, cool. Looks like we got a few answers in here. Cool. And here's just an example solution, right? Gather cooking implements and supplies. Take boiling pot out of cupboard under the counter. Take box of spaghetti out of the cupboard next to the refrigerator. Take salt from spice rack. Take oil from shelf next to stove. Then number 2, prepare water for boiling pasta. Fill boiling pot with water from the top. Place boiling pot on stove burner. Turn heat dial clockwise so that it's on high, etc. Right. So lots of different ways. So this exercise is obviously just meant to kind of whet your appetite and start getting you thinking algorithmically. One of the things, and one of the reasons we choose an example like this is one of the things when you're learning, when you're starting a programming language, a lot of you're going to be implementing a lot of concepts that you're probably familiar with, but you don't realize you're familiar with them. You're familiar with them sort of informally, right? So if you think about like all the steps involved in boiling a box of spaghetti, it could be potentially a very detailed list, or it could be a potentially very short list, like, fill pot with water, put pot on stove, turn the burner on high, fill with spaghetti, wait 10 minutes, strain pasta, serve, right? It could be very short like that, but obviously I'm skipping kind of a lot of like walking to the cupboard and like, actuating my shoulder muscles to like reach up and like wrap my fingers around the spaghetti and then pull the spaghetti down, being careful not, right? So I could get very detailed, or I could get very high level. There's a lot of different ways we could think about that. But what's important is to realize, even everyday activities, and this will probably become clear as you learn more and more to program, that you'll start seeing like everyday activities start to kind of resemble algorithmic processes. And then when you're coding, algorithmic thinking kind of reminds you of, oh, this is like, when I was looking for items in the grocery store, like check list, find item, repeat, like you have a list of items and you have an algorithm for finding each item in the store, and then you move on to the next item in the list, and then you have an algorithm for finding that. You might have ways of optimizing the list and sorting the list, and it all kind of feels like one thing. Cool. Comments, we talked about this. So I did talk about single line comments. There are multi-line comments. So when we want to do a multi-line comment, we can use a pair of triple quotes. We can use single tick quotes like this, or we can use double tick quotes like this. It doesn't matter. These are equally the same, right? So this is a comment. And if I use double tick quotes, this is exactly the same thing. So you might notice that I have these, there's just these kind of the bars of hashes and uncomment to activate, deactivate things here. So what I'm doing here is these are little code switches, and I'm using single line and multi-line comments to have little sections of my code that I can turn on and off. So I just like to do this when I stream or when I present. And then I can cover a concept and then comment out that whole block, however many lines that I did, comment it out really quick, and then move on, cover another concept. And if I want to come back to any concept at any point, I can reactivate it. So if I want to talk about printing, let's say I want to talk about printing variables, right? So my variable equals hello, and we'll print my variable. So we'll get hello out here, and then I can comment out this whole thing like that, move on to the next thing, and then come back and do this later. So I keep like anytime I do something in like Code Wars or help a student with a problem, or do one of the weekly challenge videos, I save my solution and I dump it in one of these little comment section things, and I just throw it in a notes.py file. And I have, at this point, I have quite a number of these files. I'll make a new one when it gets to like 10,000 lines long, so I can archive like my whole history of coding basically this way. So you don't have to use these comment switches. If you're confused about how they work, don't worry about it. It's something that I do and literally nobody else does. So yeah, you're not expected to be able to start doing the thing with the comment switches. Just know that that's how I'm using them, and that's why I'm using them that way. Cool. All right, so that's single line and multi-line comments. Reasons for commenting, we kind of covered this. So sending a message to someone else reading your code, either a teammate, or maybe you're on an open source project and whoever's going to read your code, you want to leave a little documentation to whoever's reading it. Exclude some code snippet from running. That's what I was talking about turning parts of your code on and off. To provide documentation for functions and other parts of your code, or to leave to-do statements. So a lot of times, you might have a lot of parts of your code that are, a lot of work that's clear that you need to do, and you want to take like, to-do statements, or you just want to write like a to-do list and come back. Each one of those to-do items might be a fairly large task, but if you're sure that you need to do those, you can come back and do those later. Okay. Also, this seems like a super obvious thing. You might be thinking like, yeah, okay, I guess I could take my grocery list there if I wanted to. I mention this because there's formal, like to do items are a formal thing in coding. So that's something that you'll hear about and it will come up. Okay. Basic constructs. Common data types, simple operations, and the assignment operator. Okay. Common data types. So that's this data types section up here. A data type can be thought of as a form in which a piece of data can exist. Working with integers, floats, and Booleans. These are the numeric types, and we'll get into what those are. There's a function, a built-in function called type, that will tell you the data type of a given object. So first of all, before we get into anything, I'm going to show you two tools, print and type. When you're solving problems, when inevitably, as happens to me and everyone else I know, we get confused while we're coding and start furrowing our brow and scratching our head, wondering what's going on. Print and type are going to be the two tools that are going to dig you out of that mess nearly every time. So print's job, you've seen me use it. You probably have inferred what it does. Print just makes something visible on the console. So in this console, this is the console in which I'm executing my code. So this is my computer's console, my bash console. terminal. And I'm executing the code with this this command. I have a file watcher called nodemon. -w dot means to watch everything in this directory for any changes. So if any file changes, it's going to execute, the command after the -x flag, right? So you don't need to execute your code this way. It requires that you install some things to get this working, but just so you know what I'm doing and why it works this way. The important part is this IPython3 and then this source document, right? So I point the IPython3 interpreter at a Python file, and it's going to execute that file. So since I said to, I guess I didn't. We'll do hello world, and I'll save that. Oops. We got an error, and it says type error. Type takes one argument. So I was calling type right here, and I didn't give it an argument. I didn't put anything in the parentheses, and it doesn't like that. It was like, what are you doing? There's got to be something in there. Okay, so when I use print, it's going to do whatever I put inside the parentheses, it's going to print the value of. Now, the value of hello world, the value of this string right here is hello world, right? So when you see something whose value is literally what is type, we call that a literal. So this is a string literal. A string is the data type used for processing textual information. We'll talk more about strings later. But let's actually talk about numbers, right? So if I want to print out the number 5, right? So nothing surprising here, right? I asked to print out the number 5, and I see the number 5, right? So 5 is a value that evaluates to surprise, it evaluates to 5. So it's a literal value, right? So if I, let's say I'll have an expression 5 minus 3, 5 minus 3 like this, that'll be 2. Right, so this is what we call an expression because it doesn't evaluate to, when I print this out, I don't see 5 minus 3. I see the result of 5 minus 3. I see what 5 minus 3 evaluates to, right? So we have the literal value 5 minus the literal value 3, which gives us the value 2. And that's what we see. So yeah. So let's talk about integers because that's a nice, easy place to start. I can save the result of some operation or some value in a variable. And the way I can create a variable, let's say I'll create a variable called a. And I can say a gets 10. So a is the name of the variable. The equal sign. This is an equal sign. This text I think maybe is a little bit small. Let me blow that up a little bit. Cool. Let's see. Okay. So this is just a regular equals operator. This is not equality. This is not like checking for equality, or it's not a statement of equality. We think about this operator, we call it the assignment operator. So we think about this as the equal sign assigns the value on the right to the name on the left. The name portion of the variable, I'll often call the identifier. So an identifier is the name, right? So a is the identifier of this variable, and its value that was assigned to it is 10. So if I print off a, Now you might have you might think, what am I going to see here? Am I going to see A, or am I going to see 10? Go ahead and put it in Slack. What do you think I'm going to see? If I print off A here, am I going to see A or am I going to see 10? Cool. It's good to see. So we're going to see 10. Well, there we go, 10. All right. So we see the value of A. Cool. So if I say B equals 5, and I can print A and B together. So if I want to print multiple things in one print call, I can pass A and B with a comma separating them, right? So I'll see 10 and 5 there, right? So what am I going to see if I print A plus B? Cool. Yep, we're going to see 15. And let's do a few iterations of this. We can add numbers, we can subtract numbers, we can multiply numbers. To multiply, we use the star operator. That's probably on your Shift 8 key for most of you. We can divide numbers. Now here's where things get a little weird. These are our basic operations. So if I look at this, I'll try to do this like this. Okay. Okay, so for this one, I got 15, I got 5, I got 50, and then I got 2.0. Now, notice how this number has a point in it, right? It gives me a fractional value back. Even though it actually, in this particular case, it doesn't need to. This is the same value as 2 without a .0 in it. When you use single slash division like this, you're always going to get a number with a dot in it like this. A number with a decimal value is not called a decimal number. It's not called a decimal integer. It's called a floating point number. We use the term floating point because the term is agnostic to the base, right? Decimal means relates to a base 10 counting system. So it's a little bit of a misnomer. As programmers, we try to think in a base neutral way often. Numbers in Python, fortunately, will be assumed to be in base 10 because if they weren't, it would be a terrible language. But we do deal with numbers in other bases. We deal in hexadecimal, which is base 16, which is really a sort of an easier way of dealing with binary. Occasionally, we have to deal with numbers being laid out in binary, and the way we prefer generally to do that is, rather than working with ones and zeros, huge strings of ones and zeros, we'll use base 16, which is hexadecimal, which has a lot of really useful overlap with binary. So being that we think we kind of leave ourselves open to thinking about things in multiple bases, we don't call these decimals, we call them floating point numbers. which makes it makes it sound potentially fancy or scary. Literally all it means is what you're familiar with as a decimal. If you need to just think every time I hear floating point number, I'm just going to think of a decimal number. That's all there is to it for now. So when you divide, whether or not the value needs to have a decimal in it, it will have a decimal in it. So let's say I do something like 4. Let's do that. Right. So 10 plus 4 is 14. 10 minus 4 is 6. 10 times 4 is 40. 10 divided by 4 is 2.5. Right. So in that case, we do actually need that decimal value. Now, if you think about it, there are sort of multiple ways of doing division, right? There's this style, which is, let's say, the most accurate, where we're going to get a decimal value that tells me like exactly what A over B is. But sometimes all we care about is how many times does B go into A. So for that, we can use floor division. So to use floor division, I use the double slash operator, division operator, the floor division operator. And that's going to give me just simply like how many times does the divisor go into the the divisor go into the dividend. And the quotient is just rounded down. So we think about it as it's rounded to the floor. And you can see that this does give me an integer back. There's another aspect to this. If you recall, like doing long division, if you were taught division like I was in grade school, doing long division on paper, and you'd get a floor division style quotient, and you'd get a remainder, right? So 4 goes into 10 2 times with 2 left over. Let's do something like this. Let's say 15, and I'm just going to comment out these other ones since we're just focusing on this. Okay, so 4 goes into 15 3 times with a remainder of 3. Is it? Okay, yeah. So if I want the remainder operator is the percent symbol. When you see this percent symbol, it's tempting to think of this as actually being like a percentage in some way. It's not at all a percentage. It's not used like that in Python at all. So that can be a weird one to get used to. It can be, like I said, it can be tempting to think, oh, well, maybe it's like what percentage of A is B? But it is literally just the remainder. You can think about this as the remainder operator. The formal name for the remainder operator, and the name that I will refer to it as from here on out, is the modulo operator, or sometimes we'll just call it mod. This is, if you want to look up modulus or modulus arithmetic, clock arithmetic, or modular arithmetic. You can look that up. There's, I think, a pretty good Wikipedia article that kind of explains it, that term and the sort of history behind that. But for now, we'll just think about it as the remainder operator, because that's exactly what it does. But it has a weird symbol, which is the percent sign. It has a weird name, which is mod or modulus. But it's a very, very simple idea. It just gives you the remainder. So, okay. So if I run that, yeah, so 4 goes into 15 3 times with a remainder of 3. Let's see, something like 6. Okay, so 6 goes into 15 twice with a remainder of 3. There we go. So we've got addition, subtraction, multiplication, standard division, floor division, and remainder. We've also got exponentiation. So this is a to the power of b. So this is 15 to the 6th. This is going to be a very large number. Oops. Cool. And to use exponentiation, we just use 2 asterisks next to each other. Some people will ask, like, how do you do, what about, if you have the complement of every other operator, why don't you have a square root operator? There is no square root operator. If you want to take the square root of something, you can either import the math library, and there's a square root function built into that. It's not so hard to do, but what I always end up doing is raising to the power of a fraction. And then your lower term in the fraction, or your divisor in the fraction, is your index. What do they call that? It's the radical. I forget. I'm blocking on the proper term for that, but it's the nth root, right? So the second root, which is the square root, the cubed root, the 10th root. So the 10th root of 15 is this, evidently, if anybody was curious. That's the 10th root of 15. Okay, so that's how you can do square roots or root operations. There's a square root. Cool. And I don't need to comment all those out. Okay. So that's numbers. So we can use, at this point, you actually have a surprisingly powerful set of tools, right? You know how to make something visible on the console. You know how to capture values, and A equals number, B equals some number. And you know how to use integers. And I just talked a little bit about floating point numbers. We just talked a little bit, touched on those. But we can use floating point numbers as well. They're not only for getting numbers back. We can actually use them in our calculations. So you can use whole numbers and decimal numbers, and we just went over all the basic operators. So basically, everything that I just went over gives you the power of a calculator, which is kind of cool. If I need to use a calculator for something, I just use Python. I just literally will start a Python shell and just use this like a calculator if I just need to make a quick calculation or something. I prefer it. I even, my phone comes with a nice little calculator app. But I went through the trouble of installing a terminal emulator on my phone, and then installing a Python interpreter on my phone that I can run through the terminal emulator, so I can use that as a calculator because I prefer it. The reason I prefer it is because I have this, I can work out of a text document. I can write down the whole process and tune parameters as I go, and kind of, it's sort of a more living, dynamic thing. So you now possess the most powerful calculator you've ever owned, at least for basic operations. Sine, cosine, tangent, all that will come later, but yeah, so you can already, using these tools, you can already kind of start using it in your daily life. And I recommend doing that. Next time you need to calculate something. Cool. So we talked about ints and floats. Those are integers and floating point numbers, or ints and floats, are what we think of as numbers. There's another type that is considered a numeric type called bool for short, or Boolean is its proper name. A Boolean has two values, true or false. So often we'll use a Boolean. I'm calling this flag because often we'll have a variable called flag that will just flag some process to run or not to run, kind of thing. And I'm lazy, so I'll just call it flag a lot of times. Yeah, so it only has the two values, true and false. So there are kind of long historical reasons that have to do with other languages and his computer history, why Boolean is considered a numeric type. For our purposes here, just think about it as something different. Technically it is considered a numeric type, but in reality, it's just true and false, and you can just kind of keep it distinct from the numbers in your head if you want. So yeah, that's the only two states. There is no like true and false state. There's no quantum physics going on here. Just one of the two states, true or false. So integers can be thought of as whole numbers, positive or negative. There's no boundary on how large an integer in Python can be. Floating point numbers can be thought of as decimal numbers. They have a fractional component to them expressed with a decimal point. There is a limit as to how precise a float can be, and precision is the number of decimal places, essentially. Well, and let's kind of look at that. So if let's say my float equals 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Something around here. I forget exactly where, but it'll break here soon. Okay, so that's presumably what I typed. Okay, cool. So you can see I wrote out this number. It's really precise. The way we would describe this is not, long. We would describe it as precise, right? The more places we add, the more precise, the more granular we're being. So we think about this as precision. So I wrote out this highly, highly precise float. I think I'm out to the 17th place here. Let's just count real quick. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So 17 places. And then I got this number, which is just 1. It's just the value 1. And this is not, you might think, oh, okay, well, Python's like, I know what you mean. I know you mean 1, it's 1. It's close enough to 1. We don't need to worry about it. I'll just make your life simpler. And, you could think about that as an advantage. That's not why this is happening. The reason that this is happening is that my CPU is physically incapable of processing a floating point value that is this precise. It does not have enough it does not have enough space in its I think it's the L1 cache in the CPU to hold a floating point number this precise. So it goes as far as it can, and it goes, this is the number 1. So my computer literally thinks this is the number 1. It's not trying to save me any like precision that might be inconvenient for me. It's up against its limit of what it's able to do. So obviously this is a text document, right? Like I can put more 9 characters here, but just when it goes to run, it's just not going to be able to be that precise. So this is not a problem. This phenomenon is not likely to cause you a problem, potentially ever, but it might cause you a problem. It's important to note that computers are finite precision machines, right? There's a limit to how precise they can be, and this kind of thing will bring them up against that limit. So should that cause you a problem at some point? If you're trying to represent floating point numbers that are like 50 places of precision or something, you're going to need which there are ways to do that, but essentially you need a custom built data type, floating point type, that is capable of handling that. Okay, anyways, moving forward. Okay, so we also talked about the type function, or let's talk about the type function. So anytime, I mean, it's obvious in this case, I'm just talking about floats. Anytime I have a data type or a variable, an identifier, whatever, and I'm not sure the type of it, I can call the type function, and I have to print the type function off. So in order for me to see it, right? So if I just call type like this, I'm not going to see anything. So it's important to remember, when you actually want to see the type, you have to print it off, and that'll tell you the type of any object. This is talking a little bit about Python's typing system, if you're curious. By type system, we don't mean like typing, like you type with your fingers on a keyboard. We mean how types are understood internally in the language. So Python's typing system is what's called duck typing. The reason that we use that term is if it walks like a duck and it talks like a duck, then it must be a duck. That's the analogy there. So duck typing means if some operation is reasonable, which is subjective, between two data types, then it should be possible. So, for example, I showed adding integers and doing math with integers, and some of those, the results of those gave us floating points values back. But I can also do mix and match floating point numbers and integers. And this might be like, oh, great, I can use numbers together. This is not a given in every language. So Python, or it's not necessarily this easy in every language. So Python makes it easy. Sort of, this is a walks like a duck and talks like a duck moment. Well, they're both numbers, so we should be able to do math with them, and we should be able to use them together in mathematical operations. I believe, let's test this really quick. Any combination of integer and float for any operation, whether you have float int or int float for plus, minus, times, divide, for divide, modulo, exponentiation. I believe if you mix and match a float and an int, you will always get a float back, I think under all circumstances. So that's kind of the thing, right? And that kind of makes sense because a float is capable of really of holding more information than an integer, right? It's more expressive. It's more accurate. It's more precise. So rather than assuming some information loss, which you have when you convert a float to an integer, right? You lose the fractional component. Python will just convert the output to a float every time. All right. I'm going to assign the breakouts as part of homework. So that was homework from the other day. Now we're actually getting into the next day. Apologies. I know so these first few days there's really a lot of material to get through. We're just covering basic topics. I'm going to forego the break again today. I'm going to just try to get through as much material as possible. Hopefully we'll get through all of this by the end of class. And yeah, but we will start having breaks in the middle of class as soon as possible. Okay, cool. So data types. So this is just what we covered. This is kind of partly a review of yesterday. Common data types, simple operations, assignment operator. Let's actually take a look back here at the overview and kind of look where everything fits, right? So we talked about some data types. We talked about integers. We talked about floating points. We talked about Booleans. We also talked about variables, which are a very simple type of abstraction, right? So variables use the assignment operator. Single equals is assignment operator to assign, let's see, identifier equals value. I say equals. I'm trying to break the habit of saying equals. It's ingrained. I'll probably keep saying equals. Really, I should be saying gets. Sometimes we'll call this the gets operator, but the proper way to say this is, identifier gets value, or A gets 10, for example, right? Yeah, and we haven't gotten into conditions or iteration yet. And that's basically what we've covered there. Okay, cool. So numeric types, int and float data types are encoded differently, but are able to share operations in Python. So this is what I was going over earlier. So let's get a little more into Booleans. Booleans seem simple. I mean, they are simple. They only have 2 values, but they are very powerful, and they show up all over the place. A lot of understanding Booleans is understanding what kind of operators and what kind of operations express Boolean values. So I'm going to show you an operator. This is the equality operator, which is it's 2 equal signs. So this is checking for equality. This is checking if the value 3 is equal to the value 5.3, which obviously it's not. So this is false. This says false. Okay. If I said equals 3.0, Do you think this is going to be true or false? 3 equals 3.0. Is that going to be true or false? Go ahead and put it in Slack. Cool. Yeah, that's going to be true. We're getting a little bit of division on this one, which is kind of cool to see. Cool. So yeah, so even though these are not equal in their type, they are equal in their value. And this is part of duck typing. This is part of the duck typing thing where Python's like, yeah, those are the same thing. Sure, why not? Other languages have a loose equality operator and a strict equality operator that checks not only if the values are equal, but if the types are also equal. So Python's equality has only one equality operator, which is what we think of as loose equality, which checks if the values are equal, but not if the types are equal. Okay. We can check if two things are equal. We can check if something is not equal. The way we see the inequality operator or the not equal operator is exclamation mark or bang equals. So bang equals, so 3 not equals 3. Is that true or false? Go ahead and put it in Slack. Is 3 not equal to 3? Yeah, so that's going to be false. Is it true that 3 is not equal to 5? Of course it is. Cool. So what we're looking at here are comparison operators. They compare two things and they tell us true or false. Are they equal or not equal? Equal and not equal operators, we can basically use those with any type, but there are some that we can really only use with numbers. So greater than, less than, greater than, or equal to, and less than or equal to. So false, true, false, true. So yeah, so greater than is going to check if, you know, the left is greater than the right, and greater than or equal is going to include if it's greater than or equal to the right. Cool. Oh, wow. We got all alternating there. Cool. So yeah, these are, don't ignore these operators. they are wildly important, especially equal and not equal. Duck typing, we just went over that. Simple operations, this is just going over plus, minus, multiply, divide. Oh, and I should really actually categorize these, right? When we, in our overview here, data types right here, right? So for ints and floats, and I'll just put these on one line here because they're so similar. So for ints and floats, when we're understanding a new data type, we can understand it by like, well, what is it useful for? Obviously, integers and floats are numbers. They're useful for, say, counting things or doing math, right? They're useful for what numbers are useful for. So, and so like, where is it useful and what type of operations apply and how do I use those operations, right? So the operations, some of the operations we looked at are, you know, plus, minus, times, divide. I'm going to stop doing commas because that kind of makes it look muddy. So divide, 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 and exponentiation. Booleans, I'm going to put the Boolean operators here. We have equality, we have inequality, we have less than, we have greater than, less than or equal, and greater than or equal. So I suggest that you keep some kind of notes like this. I mean, obviously you can deviate from this as much as you want, but every time you're learning a new type, keep somewhere, and I really would suggest writing it down somewhere, like what, every time you learn a new operation, catalog it, put it somewhere, you know, like I can use this with these, right? Obviously I'm not going into depth with these. I could, but you know, we just kind of did that, so don't need to like explain them all over again. Okay. Casting. So this is an important concept. Let's say I have A equals 3.8. And for whatever reason, in whatever problem I'm solving, I really don't care about the 8. I just want to truncate the decimal component of this, and I just want to treat this as an integer of 3. I can cast A as an integer by saying int. I can use int like a function. So I'll use the int keyword and then parentheses, and then in the parentheses, I'll put the thing that I can cast as an int, right? So this is going to give me, if we look down here, this is going to give me 3. So what am I going to get if I print A? Go ahead and put it in Slack. What's the value of A going to be? Is this going to be 3.8? Or is it going to be 3? I really sold you a trick question here. Sorry, I didn't mean for it to be a trick question, but yeah, so this is going to be 3.8. So this kind of operation, any kind of function call like this, anything that looks like this, isn't going to cause, it should never cause, and in the case of integers and floats, can never cause a change to the variable, right? So what this is going to do is it cast kind of makes you think that it's going to like change that identifier's value, that it's going to alter it in some way. It doesn't. It just gives me, it's like, oh, give me an integer version of A back. What would an integer version of A look like? Like, oh, if I converted A into an integer, it'd be just 3. So it's going to give me that back, and I'm going to print it. But it doesn't actually alter A. So, and this is an important concept. I'll be touching on this as we go. This is mutability versus immutability. Pay attention to those terms as they come up in Learn, and we'll be covering that concept later. So this is going to give me 3.8. Sorry for the trick question. I didn't mean to get a cheap trick over on y'all. Now, if I did want to change, you know, maybe I don't really care about the value. I could reassign A. I could say A equals an integer version of A, right? And all this is saying is give me the integer version of A and then assign that to A. So the right-hand side evaluates first, and then that we get a value out of that, and then that gets saved in the same variable name, happens to be the same variable name. So it overwrites the 3.8. So this will change the value. This will change the value of A. So if I print off A now, it'll be 3. So sometimes you want to change the value. Sometimes you don't want to change the value. Depends on the problem, depends on the way you want to solve it, depends on personal taste, whatever. Cool. We can also do something similar. I'll just get rid of these prints real quick. we can also cast we looked at casting a float to an int. B equals, let's say, 57. Okay, I want to print off a float version of B. Feel free to get this wrong. There's no right answer, but let's see a little brainstorm. What might I put in this print to what do you think I might put in this print to get a float version of B, and what would that float version of B look like? Oh, that's a good guess. We want to do the action to B though. Although, in your defense, that will give us the same the same result. So, I'm being pedantic. I'm sorry. So print float B 57.0. 57.0. Cool. Yeah, exactly. Right. So I can just use float, float, put some parentheses after it, and then pass into the parentheses. When we put something in the parentheses, we call that passing in, like handing it over. So we'll pass in B, and that'll turn it into a float of 57.0. And just to be clear, if I print out B, no change is made to B because I didn't ask for there to be a change made to B. Cool. So as we explore other data types, every data type that we explore will have a function built in that we can cast certain other types to that type, right? Not every type will be able to be cast to every other type. So sometimes you have to do weird things, kind of juggling things around. Apologies, let me read this question here. Does casting have limitations on what data type? Oh, hopefully, yeah. I just answered that. Cool. Wang gave me grief. Trace back. 1, 2, 3. You can call float float object is not callable. Well, float object definitely is callable. Are you? Huh. You might be using an older version of Python. This might be an error with Python 2. L. No. You can try running this code. If you get the same error, DM me and I'll see if I can help you out with that PR. Cool. Okay. So yeah, we'll be able to. Oh, it's in Replit? You're getting that error in Replit? That is really weird. Float objects are not callable. Huh. I know. It's probably like really obvious, but I'm not seeing it somehow. Or, this is also possible, Replit is having problems, which it does occasionally. Okay. Cool. This is a shorty breakout. Let's do this one. Okay, good. It looks like it worked for you. and go ahead and put in your code and the solution or the results of that code when you're done. Okay. Feel free to keep working on that. I am going to paste a solution in. If you don't want to look at it, then I guess don't look at it. I'm going to share my screen again. To find the thing every time. There we go. Okay. So moving on. So we already kind of talked about floor division. We already talked about modulo. Quick note on this. Returns the remainder after dividing y into x. So it turns out that modulo, I think people look at this and they're like, oh, we get this weird, goofy little operator that, that's there should you ever have a weird scenario where you might need to know the remainder of something. You use modulo all the time. Yeah. You can use it for seeing if something is divisible by something else. So I'll show you what I mean. Let's say I have some variable A, I don't know what it is, some variable B, and I don't know what it is. I'll give these values here in a second, but we'll just pretend like these are two values. We don't necessarily know what they are. And I want to see if B is a factor, if it's a divisor of A. So if A mod B equals 0, then B divides evenly into A. So there's all kinds of stuff that you do where you want to do that exact thing. So let's say let's pick a number and we'll do that. So false. 23 is not a divisor of that. I don't know what this number is. It's just some silly huge number. But 2 is going to be a divisor of that number because it's an even number, right? This is also another really useful thing. If you want to see if a number is even or odd, right? If you want to see if a number is a multiple of 3 or a multiple of something else, right? So it can be really useful for seeing it, like how numbers are factors of each other, right? So don't forget about it. Don't underestimate little modulo over here. Okay, using modulo with floats or negative values is valid. Python, I don't really know that it's come up for me. You get some kind of unexpected behavior. You get these kind of long underflows, precision errors, right? With these long strings of numbers. Sometimes negative modulo, you don't need to worry about it. Should you cross that bridge, someday, then I guess you'll cross that bridge when you come to it. Okay, cool. I know I'm kind of moving quickly with the breakouts. The value, I think, is to just spend some time doing them. You can always redo them, and that's actually pretty useful. Even if you know the answer, you can redo them and get a lot out of them that way as well. Yeah, let's do this one as well. This one I'll give a little extra time for. I think we're actually doing good on time. Cool. So there's that one, and I'll put 3 minutes on the clock. Also, feel free to put a question in Slack if you've got one. If you put @Clark in front of it, I'm more likely to see it quicker. See an answer in there. Print 3 mod 299. Did you run that? And does the result seem seem valid? I suppose I should mention this. As you all are solving problems, I think it's tempting if you're new to I'm sorry, I don't mean to put anybody on the spot here. That's the timer as well. So go ahead and keep working, but I do want to cover this. When you're new to programming, or there's certain schools of thought in programming pedagogy that I disagree with around this particular thing. I'm trying to describe the approach that some people will want to take, where you write out the code and like you think about it, and you're really thoughtful, and you're going to make sure that it's going to work before you run it. I can't, there's not an, I can't overemphasize the importance of kind of getting away from that way of doing things. And I know that, I'm just going to be opinionated about that. It is my opinion, and people do work differently, but in general, it's not bad to think through problems and understand your code. I don't solve problems that way. I don't know any working programmer that really does. What we tend to do is kind of guess and calibrate. Throw something at the terminal, look at it, see, does that seem reasonable? And print it out and print it out and print it out and print it out until you've verified your results by doing that, right? So you can kind of use that process to proof what you're doing as you're going. And that's something that you'll just get used to as time goes on. Cool. So there's the, did that paste in right? Yeah, there it is. Yeah, so there's the solutions in there when y'all are ready. Oops, and I got a screen share. Where's this one? Okay, so casting. I didn't talk about casting things to Booleans. You can cast every data type in Python to a Boolean that I'm aware of. So this gets into something called truthiness and falsiness. Every value, no matter what the type, has truthy states and falsy states. Some people get really into this. I would not spend a lot of time on it, but you will see it. So to me, it's, I think, a strictly unnecessary feature. It's something that I don't really use, but it's out there. So just so you know, if I try to cast a bool of a number that is not zero, any number that's not zero, positive or negative. I didn't talk about negative numbers, but we can use negative numbers too. So any number, float, int, oops. Positive, negative, doesn't matter. If it's zero, it's going to be false or falsy. Zero is falsy. Anything that's not zero is truthy. So notice negative 0.003. That's not zero, so it's truthy. Yeah. Assignment operator, we talked about that. That's just your quality operator. Incrementation. So it's really common that you'll have, you'll start off, I can call this variable anything that I want, so long as it's not like a built-in keyword that's already reserved by Python, right? So I wouldn't want to call it print or something because there's already a function called print. It's a weird thing. Python actually will let me call a variable print and then just override the print function with the variable print until I delete it or something. So you just have to know not to do that. Otherwise, you're just not going to have a print function until you change the name of that variable. So I'll call this counter. So let's say I want to count things, and for whatever reason, I want to increment my counter. So I want to say counter equals its current value plus 1. So counter equals counter plus 1. So if I print counter, Actually, I have to use all the characters. Okay, so I just added 1 to counter, and as many times as I run counter equals counter plus 1, it'll add 1 that many times, right? So this, again, right? So this is an assignment to the same variable, and I can reassign variables arbitrarily. If I wanted this to be foobar, I could do that, right? It doesn't have to have anything to do with its prior value. I can reassign variables to whatever I want, whenever I want, right? So, and I can even include the variable's current value in the on the right hand side. So the right hand side will evaluate first. So counter plus 1 is 0, plus 1 is 1. So counter equals 1, right? So now counter's value is 1. So the right-hand side will evaluate first. Counter is 1 plus 1. 1 plus 1 is 2. So counter equals 2. Same thing, right? Counter's value is 2. 2 plus 1 is 3. Counter's value is 3. So that's what's happening there. So this is such a common thing to do that Python gives you a little shortcut. It's called syntactic sugar, which means it's just a little bit of syntax that makes some slightly clunky process a little sweeter, a little nicer, right? So if I want to increment a value, and I don't have to use 1, I could use 4 or 3.9 or whatever. I could use anything that I could add to a number, any other number I could add here. I can say counter plus equals whatever my desired increment is, right? So this is exactly the same as this. When Python sees this plus equals, it goes, oh, I know what that is. I'm literally just going to rewrite that as this, right? So it's going to write this this to that, right? So it's going to rewrite this line 106 to exactly what you see here on 107. That's all it does. And the convention is to use the plus equals way when you get away with it. We don't just have plus equals though. We have this operation for any operation. So we could do minus equals, which would convert into counter equals counter minus 1, right? We could do, I mean, you probably see where I'm going with this at this point. We can do times equals. We could do divide equals. We could do floor divide equals. We could do modulo equals. Or exponentiate equals, whatever. So we can do any of those. I don't even know what the value is. Okay, so counter is just 0 at this point. Probably makes sense. But in any case, whatever operation we're using, it just rewrites it in the long form. And what I mean by that is the interpreter literally rearranges it into the line underneath internally, right? So it's understood, counter plus equals 1 to the interpreter is understood literally as counter equals counter plus 1. So those are the same. If you're just starting out, you can use whichever one makes sense to you. But yeah, like I said, the plus equals is convention, and that's what I'm going to use. Scalar types. So scalar types, a scalar type holds one single value. So this is a classification of a group of different data types. So integers, floats, and bools, everything we've talked about thus far is a scalar type. Other scalar types are strings, which I've mentioned a little bit. The none type, which is a unary type, it has a single value. Boolean has two possible states. None has one possible state, which you might guess is none. Complex and byte are also built-in scalar types, but we're not going to actually get into those into this class. Integers are whole number values, positive or negative. Like I said, I haven't really covered negative numbers in order. Let's just look at this since I kind of forgot to do it. If I want to make a negative number, just -6 is -6. Just throw a negative sign in front of it. There are certain times, like if I wanted to do like -6 times 5 or something. Convention is when you have a negative number like this to just throw parentheses around it, and then it just helps Python not get confused about whatever maybe is around it, right? So if I have like 4 plus -6, like this is, this is kind of looking weird. I don't know. I'm not even sure if this might give me an error. This does work, but yeah, convention is still, if you have a negative number just hanging out on its own like that, just throw some parentheses around it, and that'll kind of help Python be able to get around any errors that might crop up. If you're familiar with PEMDAS, the order of operations, parentheses, exponents, multiplication, division, addition, subtraction, PEMDAS. That is the order of operations for Python as well. Okay. So yeah, like I was saying, integers are whole number values, positive or negative. Floating point values, numbers can also be positive or negative as well. Underflow is that thing I was talking about. I forgot to mention that it's called underflow. When a value becomes too precise for your machine to be able to handle, that's called underflow, when it just turns into something else. So a float can be thought of as a continuous, while an int can be thought of as discrete somewhat. Sometimes we consider two floating point values to be essentially the same, equal, if the difference is below some threshold. Underflow occurs when trying to represent a number that is smaller, I would say more precise than the computer is capable of representing in its binary registries. Can lead to unexpected behavior. It's not likely to, but it can. Like I said, you're not likely to encounter this as an actual problem within this course or for a long time. But if someday you do encounter that as a problem and you don't know underflow can occur, I had a friend who was a pretty accomplished programmer and didn't know about underflow and ended up spending days on a Java problem, and then learned about precision limits. So yeah, anyways, Booleans or true or false can be considered 1 or 0 when cast to a numeric type. I kind of forgot to show that, but if I cast true to an integer, I'll get 1. If I cast false to an integer, I'll get 0. And we didn't go over, shoot, did we? Okay, I don't think this covered logical operations yet. No, we'll cover it next time if we don't cover it today. So not, if I have true, there's another keyword. Now, not is not a value. It's a keyword, and it negates a Boolean. So not true is you might guess false. Not false is true. So this can be useful sometime. So the result of the comparison operators that we looked at are Booleans. Strings we looked at just a little bit. So a string is an object that acts as a sequence of characters. So it's Python's way of dealing with text. So when we want to deal with textual information or information in its textual form, we can use the string data type to do that. So in order to use a string, you've seen me do this a little bit. In order to use a string, we can just use quotes. So I can say my string equals hello there. Print my string. Cool. My number, we could say, equals 348 times 57. And let's do my number. I can cast my number to a string with the str function, str. So str my number is going to give me a string of this integer. Now, notice it doesn't look any different, which is kind of silly, I think. I wish they would include the quotes around the number, but that is a string, I assure you. We can actually prove this, though. Let's say I want to divide this number by 2. Well, I'm going to get an error. Oops, I got the wrong error. Okay, I forgot to comment that out. Okay, this is the error that I was expecting. So even though that looks the same when I print it off, it's a false false string there. Oops, didn't mean to bring this. Okay, there we go. So if I try to do math on that number, since it's a string, I get this error, type error, unsupported operand types for / between str and int. This is a good opportunity to re-mention, as I will be mentioning multiple times throughout this. Errors are really useful. They help you do your job. You're gonna want to learn to code in a way where you get errors intentionally to find the bounds of a problem. If you get all the errors while you're developing something, then when you deploy it, you can have more confidence that it's been put through its paces, right? So code in such a way that you want to get errors, and you do. I assure you do want to get errors. The more errors you get, the more you familiarize yourself with the errors, and the easier it becomes to solve those errors, right? So notice this error output, and this is fairly typical. Your error output might look different. It will look different in Replit. Mine is nicely highlighted and kind of fancy looking. The most useful information for an error message is at the bottom, and I found this out the hard way by reading the top of errors all the way down, a whole bunch, until I was like, none of this is helping me. I'm not getting any useful information until I would read the last line, and I'm like, oh, I think I know what to do with that. So always just look at the bottom line, and then if that doesn't help, go up to the next section, and that'll point at the line in which it finds the error. So it says line 146, print right here, and that can help you locate where the error is happening. Cool. Looks like we got a couple questions here. I'm going to take these after class because I do want to wrap up. So if you all don't mind just hanging out for a second, and I'll take those questions real quick. So strings. I want to talk a little more about strings. So we can use single or double quotes. Single tick quotes like this. This is, I think, what most of you are familiar with as the apostrophe key. In Python, it's a single tick quote. Double tick quote, there's no difference. One is not like one kind of string and the other is another kind of string. They don't have special purposes or like a niche that the other one doesn't do. It's just whichever. So there are two ways to make strings. The Pythonic thing to do is to use single tick quotes. That's the formal Pythonic thing to do. I don't like to use single tick quotes. I like to use double tick quotes. I think they look better. And I often want to use apostrophes in my strings, which if I say like theirs or something, I can put an apostrophe in my string without it conflicting with the single tick quotes. If I wanted to put an apostrophe in a string delimited by single tick quotes, I can do that, but I have to put a backslash in front of the apostrophe, which just looks weird. So I find myself using apostrophe characters in strings fairly frequently, whereas I don't find myself using quote characters in my string that frequently. So I use double tick quotes. That's sort of a stylistic choice. You don't have to do everything the most Pythonic way. The most important thing to do is to be consistent. But like Pythonic conventions are generally really good. And I think I probably follow most of them. But you'll develop your own aesthetic preferences and your own coding style. My coding style is quite a bit different than Tovio's. And everybody else is on my team. And we try to standardize somewhat, but there's still enough wiggle room. We can always kind of tell who wrote what, and that'll develop for you as time goes on as well. One more thing, there's something called concatenation. We can do, so if I print, concatenation is a fancy word that we use for adding two strings. So if I say hello, I can say hello plus world. And I could break this out. Name. Something like that, right? And then these two strings are concatenated together. And to use concatenation, we can use the plus operator like this. Cool. We'll wrap up here. So we're basically through today's material. We just have the none type to get through, but that's not a big deal. We'll just touch on that first thing in the next class. So I see a couple questions in here. I saw somebody asked a question. It looks like they deleted it, but yeah, we'll open it up for questions. You can feel free to go if you're done. You want to rest, get out of here, have a good rest of your night. I'll see you tomorrow. Feel free to DM me. I'll get back to you as soon as I can. But yeah, feel free to hang out and ask questions too if you like. Let me stop the recording.